Hello everyone, and welcome to my session. So I'm so excited to be here at SREcon, so a conference I've always respected. Thank you so much for giving me this opportunity. So this is the agenda for today, and let me start from the introduction part first. For nearly a decade, I've been an SRE focused on keeping complex distributed systems running. But recently, my career took an interesting turn, so I joined the platform network team. So it's an interesting place to be because it's where our fellow developers often come to us with a very familiar phrase. We think it might be a network issue. Yeah, so we are expected to have an answer because we are supposed to be experts. So we look into the issue and very frequently. So it has nothing to do with the network. So yeah, because we run distributed systems, so every interaction involves the network. So the network gets blamed when people run out of other clues. I want to change that. So I believe we all need a way to provide definitive, data-driven answers, so not just to prove the network's innocence, but to find the true root cause wherever it might be. So this talk is a result of that experience. So it's not about turning you into a network expert. So it's about equipping you as a fellow SRE, so with a set of practical techniques to get the data you need, so which are ready to use in your next investigation. And before we dive in, so I want to set two clear expectations for our session today. First, our focus is specifically on the Kubernetes environment. So we won't be covering general packet capture on bare metal or VMs. Second, this talk is about one thing. So how to reliably capture the right packets. So deep packet analysis with tools like Wireshark is a huge topic deserving its own dedicated session. So our goal today is to get you the raw data you need to start that analysis. And also I have a disclaimer. So packet capture can expose sensitive information. So please be mindful of data privacy and security implications, and always follow your organization's policies. So with those in mind, let's begin. So let's look at what's really happening between your applications and the network. So as site reliability engineers, a huge part of our job is managing systems built on layers of abstraction. So our application code is written with a certain set of expectations about how the world works. For networking, it expects to send and receive a reliable ordered stream of data. So we achieve this through abstractions like the TCP socket. So our code interacts with this clean API, assuming it will handle the details. However, beneath this clean API lies the complex reality of the network. So we use the term best effort to describe this underlying reality. And it's when the nature of this best effort system leaks through our abstraction that many of the most difficult production issues occur, creating complex failure modes. So let me tell you two examples of this best effort reality to illustrate why this necessitates packet level observation. First, so there is no guaranteed latency or delivery order. So packets can be delayed, dropped, or reordered due to countless factors like buffer bloat in a switch or routing changes. To your application, this doesn't look like packet loss. So it manifests as a mysterious, jittery pause in execution. So you see the effect, but not the cause. Second, there is no guaranteed throughput. So the rate at which your application can send data is not a fixed value. So it's a dynamic variable controlled by TCP's congestion control algorithms. So if the kernel perceives packet loss, it will autonomously shrink the congestion window. So your application metrics will simply show a sudden drop in throughput, but the decision was made deep inside the kernel. So these are not bugs. So this is the network operating as designed. To diagnose problems that originate from this inherent probabilistic nature, so we need a tool that can observe it directly. So we need packet capture. So then let's move on to the main topic. We will look into how we can perform packet capture in a Kubernetes environment. So we will explore 3 primary strategies ordered by their increasing proximity to the application. So our first strategy involves the techniques executed directly on the Kubernetes nodes. So this is the least intrusive approach, as it doesn't modify the running board at all. A critical prerequisite for this entire strategy is that you must have shell access to the Kubernetes nodes, typically by SSH with sufficient privileges, which is often root, to run diagnostic tools. So this is a significant requirement and may not be possible in all environments, so especially in managed Kubernetes services. So assuming you have this access, the on-node strategy offers 2 distinct observation points, so each for different purposes. So this diagram illustrates the node's network structure. So there are pods which have their own network namespace and the root network namespace for the node itself. And the first observation point is outside the pod's network namespace. So by capturing on the node's main network interface, so which is usually Ether0, and filtering by the pod's IP address. Sorry. So the workflow looks like this. So first, so you will identify the name of the node and IP address of the target pod. And then so you will SSH into that node. And finally, on the node, so you will run TCP dump on the main network interface and with filtering by the pod's IP address. So let's break down that TCP dump command. So -I tells TCP dump to listen on our target network interface. And -n tells it to skip DNS name resolution to prevent it from generating extra DNS traffic of its own. And -w tells it to write the raw packets to a file named capture.pcap, which we can later analyze with tools like Wireshark. And finally, so the expression host and port IP. So this is a BPF filter. So it's a small expression to tell the kernel to only send us the packets that match this filter. In this case, we are asking for packets where the source or destination IP is our port's IP. So this technique is essential. So when you suspect the problem is not inside the application container, but in the infrastructure that the node provides to the container. So let me give you some examples of these node level issues. So first one will be that port A can't reach port B on a different node. So your hypothesis might be that the overlay network is failing. So capturing on the node's physical interface allows you to see the encapsulated traffic like VXLAN and verify if they are being sent and received correctly. And another example will be that network policy is unexpectedly blocking traffic. Your hypothesis is that the CNI plugin, like Calico or Cilium, is misconfigured. Since network policy enforcement happens at the node level, so often using IP tables or eBPF, so capturing on the VEs interface, let's see if packets are being dropped before they even have a chance to enter the pod's namespace. So in those cases, the problem lies in the fabric connecting the pod, not in the pods themselves. And the next observation point is inside the pod's namespace. So we use NSEnter on the node to execute TCP dump within the context of the pod's network namespace. So this technique is for when you suspect the problem is happening inside the pod's own network stack. This time, the workflow looks like this. So again, so you will SSH into the node first, and then on the node. So you will somehow identify the target pod's PID, so process ID, so using the command CRICTL. So you don't need to dig this deeper for now, and I am not super familiar about this, but so you will somehow so look up the process ID of the target pod. And then so you use NSEnter to run TCP dump inside the pod's network namespace. So when to use this, so in contrast with the previous approach, so you use this when you suspect the problem is inside your application container. So here are some examples of these import issues. First will be that your application fails to start or complaining it can't bind to port 8080. So your hypothesis is that another process inside the same port is already using that port. So using NSEnter to run netstart inside the port namespace can confirm this. And another example will be that service mesh sidecar, so like Istio, is causing issues. So your hypothesis is that the application is sending correct plain text traffic, but the sidecar is mishandling it. So you must be inside the port namespace to capture traffic on the localhost interface between the application and the proxy. So capturing on the Ether0 from the outside would only show you the encrypted MTLS traffic, which is useless for this kind of debugging. So to summarize the on-node strategy, so you use the outside approach to debug CNI and overlay network issues. And you use inside approach using NSEnter to debug the application direct network behavior. So the main trade-off for both is that they require root access on the node. So now, so let's look at approaches that rely more on the Kubernetes API. Excuse me. So yeah, our second strategy is an interesting approach, so centered on convenience, so exemplified by tools like ksniff. So the core idea is to run the capture process inside the target container without requiring a pre-installed TCP dump. So it does this by using a combination of kubectl primitives, so kubectl CP to upload a static TCP dump binary into the running container's file system, and kubectl exec to run it. So it's a kubectl plugin, and you can install it easily using Crew, so a kubectl plugin manager. So once installed, you can invoke it easily in a very similar way with other kubectl commands. So this provides a very appealing one command to Wireshark workflow and gives a same network view as the port by capturing inside the port. So the workflow looks like this. So yeah, first, so you will identify the target port, and then so you will run the kubectl sniff and give the namespace and give the name of the target port, and that's it. So by doing so, the ksniff will launch a TCP dump process so within the target port, and then its output will be piped into locally run Wireshark. So yeah, Wireshark will start locally and capture will start very soon. So it's very convenient. So however, it's important to understand the downsides. First, so it is stated as non-production ready. So it may not be a good idea to use it to investigate production issues. Second, so you are modifying a running containers file system, which may have security implications. And third, there can be a compatibility issues between the static binary and the containers environment. So it's a clever technique, but one to use with awareness of its trade-offs. So this brings us to our third and most useful strategy. So using ephemeral containers via kubectl debug. So this is the officially supported Kubernetes native way to attach a debugging environment to a running pod. It's worth noting that this feature requires a relatively modern Kubernetes cluster. So ephemeral containers were enabled by default, starting in Kubernetes 1.25. So if you are on an older cluster, so this specific technique may not be available to you. So now let's pause and understand what this command actually does. So when you run this, you are telling the Kubernetes control plane to perform a special action. So it does not modify your original container. So instead, the control plane schedules a new temporary container, an ephemeral container, to run inside the target pod. So the key mechanism here is that this new container is launched into the same network namespace as the application container. So, but it has its own mount namespace, which means it has a separate file system tree from your application containers. So this is what makes it perfect for our task. So we get a clean, free-featured debugging environment that has the exact same network view as our application. And we can achieve this by using the purpose-built image NetShoot. So it's essentially a Docker container packed with dozens of networking tools, TCP dump, dig, nmap, so everything you might need for network troubleshooting. To give you a real sense of how this works, I've prepared a live demo of this strategy. But so this is a live demo, so please don't expect that this works flawlessly. So yeah, I have. Yeah, so for this scenario, our objective is to troubleshoot high latency in an application. And I have a simple application deployed in a local Kubernetes cluster. So I borrowed the demo application from the popular book, so it's still in action. So let's see how it looks. Yeah, here I have it opened, and I am hitting the reload here. It's loading. So yeah, it works, but so it was a bit slow, so right? So also I can open it in the terminal. So using curl, throwing away the output, and yeah, it took 4 seconds to get the response. So, and it isn't expected. So, as the application is very simple. So, what's going on? So, we have several seconds of delay, but no other clues. So, let's use kubectl debug to get inside the pod and start the general packet capture to see everything that's happening on the network. So I execute kubectl debug command. So I have the command prepared. Basically, so this will run kubectl debug on the target port and giving some options and using the netsuite image and launching a TCP down process and letting it generate output to standard output and piping it to locally run Wireshark. So let's do this. So the Wireshark started and capture also started. So let me reproduce the throw request. This. I think we got it captured, so stopping the capture. So yeah, so the output of Wireshark looks like this. So yeah, now so we have our evidence in the Wireshark screen. So the capture started, and we received a HTTP request from the browser. This one, and this demo application is built on a microservices architecture. So several requests are made, and finally, so it is giving response to the browser. So that is what's happening. But as you can see, we have several DNS requests, right? So yeah, it didn't go so smoothly. Like so, I got a health request in between. So the output is got a bit confusing. But so basically, so the DNS request was made to here, and I can find a better place. So yeah, so DNS requests are being made multiple times, but so they are going to different IP addresses. First, so we have DNS request to a strange IP address, so which is to 10.42.42.42. So then 1 second of silence. So you see the timestamp. So there's 1 second gap between this and this. And then DNS request is made to this IP address. And finally, so we are receiving the DNS response. So basically, so this 1 second was wasted. And from this web app service, several requests are made, resulting in the total of 4 seconds. So now that the packets have given us a proof, so we can confirm this by looking at the pod's DNS configuration. So we will get into the pod now. Please hold on. Okay, I am running the kubectl exec, and I am showing the what's in resolve.conf. Yeah, so there's the answer. So as you can see, the first name server is a black hole IP. So the problem I intentionally configured for this demo. So the resolver tries this server, waits for the timeout, and only then falls back to the working server. So yeah, as the demo shows, kubectl debug allowed us to get into the location needed to capture the truth. So the packet data didn't just show slowness, so it showed a specific DNS query timing out after 1 second before successfully deployed to a secondary server. So this level of detail is what allows us to move from the network is slow to an actionable root cause. Finally, so I want to touch on the future, so which is already here, so eBPF. So eBPF changes the game by allowing us to run sandboxed programs directly in the kernel. So there are also standalone eBPF tracing tools like BPF trace. So they are great for understanding what the kernel is doing, but they are not a replacement for packet capture. Now, the more transformative part is what happens when eBPF is integrated into the platform. To show you what I mean, so let's jump into a quick live demo with Selenium and Haplon. For this demo, I am using a cluster with Selenium CNI installed. I'm going to open Haplon UI and sorry. Okay. Okay, so what you are seeing here is a Haplon service map. So this one is too small, but so this is generated automatically and in real time based on network traffic. So it instantly shows us what is talking to what. So now, so remember the slow application from our last demo. So I have it running here as well. So let me send a request to the application again. So on the map. So we can see web app is talking to catalog, forum, and kubedns. But also, so another box, so labeled as world on port 53. So this world represents traffic leaving the cluster to an IP address that Haplon doesn't recognize as a port. So let's look at the low flow data at the bottom to see what's really happening. So it's a bit small again, but yeah. So let's see these entries. So yeah. So we can see web app is sending DNS query to destination IP 10.42.42.42 on port 53. And this is a black IP from our DNS misconfiguration. And right after it, we see another request going to kubedns service. And we have a timestamp here, but it isn't visible. But so between this and this, so there's 1 second of gap. So yeah, we are seeing evidence of the fallback behavior. And this table view can get noisy. So but Hub is also good at filtering. So let's say if we want to prove that the problem is this black IP, so I can go to the filter bar and ask Hub to show me only the traffic going to that specific IP. Here like this, so the table are now filtered to show only the failed DNS attempts. So we can see web app is the source. So this confirms which application is affected by this misconfiguration. So how does this connect back to the theme of packet capture? So this shows us a new workflow. So we use the high-level tools to visually confirm the DNS issue. So now that we know the what and where, so we no longer have to guess. So if we still need the raw packets, for example, to measure the precise timing, so we can now perform a surgical targeted capture, so filtering for port or 53 on the web app port with confidence. So this is a key point. So using high-level observability to move from speculative capture to targeted capture. So what is the takeaway? Yeah, so there is no single best tool. So there is a toolkit and a set of strategies tailored for different problems. So let's recap. So the first strategy was the on-node approach. So this requires the root access on the node. So and you use Ether0 on nodes when you need to see traffic as the node sees it. So which is perfect for debugging CNI or overlay issues. And you use AnyCenter when you need to see the traffic as the application sees it without modifying the port. And the second strategy was the binary approach using ksniff. So consider this as a convenience-focused tool. So it's an interesting technique and comes with convenience, but be mindful of its intrusiveness, which you might not want for production clusters. And the third strategy was the import approach using kubectl debug. So this is the recommended Kubernetes native approach because it offers the best balance of flexibility and ease of use. And finally, so keep an eye on eBPF. So it represents the future of low overhead intelligent network observability. So my goal today was to give you that toolkit to arm you with the techniques to get the data you need. So now, so you should be an SRE armed with a toolkit to prove with data. So you will be ready to answer the question. So is it network? So it may or may not be the network, but now you have the way to answer. That's it from me. Thank you.